Hi guys, let's talk about symmetry today. You're probably going to come across this if you're in inorganic or organic chemistry. Whenever you are, God bless your soul. But symmetry is really going to be an important topic in these courses because, well, molecules have symmetry, and it's a good idea to at least understand symmetry. Maybe when it comes to NMR, I'm sure all of you watching this video have seen NMR. So if you have equivalent hydrogens, how can you prove that? For example, that's going to be this topic of symmetry. Now, symmetry can be described qualitatively, like we have been showing, where we say, okay, you do it, you flip the molecule, there's a plane of symmetry there. Okay, that's fine. But what if we want to publish symmetry in a paper and we want to say it has blah 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 symmetry? Well, you could say it as a plane of symmetry, or you could use a very mathy kind of way. And to do that, you're going to use symmetry operators. We have them here. The Cn operator, the sigma operator, the S sub n operator, the I operator, or the identity operator E. And you can use this, and you can use this terminology to describe symmetry. Now, it gets mathy, so if you get into the math of symmetry, you'll see these used. And in proofs of symmetry, you'll see these used. But in our talk of inorganic or organic, we're just going to look at this more qualitatively, but understand that there's math behind it. Okay, so let's go over each operator and talk about what it means. So for Cn, it's the rotation operator. It says if I rotate a molecule some number of times, I can go back to 360. And at each stopping point, which we'll see is the value of n, I'm going to have unique symmetry, basically. The best example to show this is borotetrahydride. So if I draw this here, and imagine we have a little pole sticking out the top. This is going to be called, if we rotate around this axis, we're going to call this C3 symmetry. So what we define n to be, or 360 over n, the angle of Cn is going to be 360 degrees over n. So in this case, if this is C3 symmetry, well, 360 divided by 3 is 120. So what this is saying is I can rotate about this axis clockwise or counterclockwise 120 degrees, and I can get an exact replicate symmetrical molecule to this. And hopefully you can see that, right? It's making kind of that peace sign, right? Trigonal planar, how you've seen it in the past. If I were to rotate this, right? Maybe, for example, this bond is being rotated clockwise. So he's going to end up where this hydrogen was, and this hydrogen will end up there, and that hydrogen here. And you get a symmetrical molecule. And you can do this 3 times, rotating the molecule 120 degrees, and you'll get a symmetrical molecule. That's the idea of the Cn operator in essence. It's a very simple one. But notice, C3 is not the only rotation operator. We also have these ones too, and they're a little weird to draw, but typically you might see it like this. And this would be C2. You can flip the molecule over on itself and then back and get a symmetrical molecule. So this would be a 180 degree rotation using that formula there. We can also do this for all the other hydrogens. They also have C2 symmetry. And this idea is going to become a little bit important when we get to some future topics with this idea of point groups and assigning quick point group identities to molecules. But that is the rotation operator. Now I want to get into the sigma operators, and they can be a little daunting to realize and memorizing in general because there's 3 of them. But we need to define that principal axis. Wherever Cn is the highest, that's the principal axis. So in our example, I already erased it, sorry, but the trihydrogen boron thing that we looked at, or boron trihydride, what we noticed with that was that C3 was the highest number for n. So whatever gives you c to the highest n, or subscript n being the highest, no other real way to say that nicely, that is going to be your principal axis. So let's just say we have some Cn that is also the principal axis. And let's say I'm just going to omit any ions, or just letters and distinguishing elements. I'm just going to write X, X, X. So hopefully you can see this is exactly what we had before. And we have that principal axis of rotation here. However, there exists these planes of symmetry. This is what sigma is going to describe, planes of symmetry. Basically mirrors. So if I have a plane of symmetry right here, I would expect to see another one of myself right here. It's really simple. I hope that you've seen mirrors in your life, just living your life. What sigma h is perpendicular to Cn. So if there exists a Cn, there might be a sigma h. And sigma h is the plane of symmetry described here. So I hope I'm doing a good job of describing it, but it sits over all of it encapsulates and covers all these X groups here that we see. So this is going to be sigma h. There can also be sigma v and sigma d. And whereas sigma h was perpendicular to the principal axis, right, sitting like this if we were to look at that as straight up and down, what sigma v and sigma d are going to do is they're going to pass through the line of the principal axis. So what does this look like? Well, for sigma v, it will look something like this. So here's our principal axis, Cn, and we have our groups. Let me just draw them like I have been. We have our groups. If they sit on you could think of it as the ligands or the atoms themselves that are projecting from the central atom, we call that sigma v symmetry. So it would look something like this. I'm going to do my best to draw this. I'm probably going to fail. We'll draw this one first so you see the idea. So this plane is directly flat. I should probably draw it like this to show that it's a plane like that. So hopefully you can see it's completely flat, encapsulating this X. But there's another one too, and it's going to, let's say this group going back, we can draw a plane of symmetry there too. So hopefully you can see I have a plane going like this, but I also have a plane going like this. But now there's also this plane too. So this plane, here's our initial sigma v. That plane is going to come out this way. So I'm going to draw this so bad. Oh my goodness. I said I wouldn't do it, but I did. Hopefully you can see that plane is now coming out and encapsulating this X group here. However, there also exists, if sigma v exists, then sigma d exists. And sigma d is like sigma v, but it's in between the atoms. So sigma d, we have that principal axis of rotation. We have our ligands or our atoms, whatever we're focusing on. But now we have planes of symmetry in between. And would that be, could we have those here? I'm trying to think. No, you couldn't do that. You couldn't do that. So for a trigonal planar one, you can't have a sigma d. So let's actually modify this such that we have this kind of configuration. Well, then we actually have two sigma d's. And what sigma d looks like is they're going to be in between axes. So for example, we have a plane here, and then we would also have a plane going out like that. It looks something like that. So we have it's going right on. I have to draw it on a little bit of an angle, but it's going straight into the principal axis. This one's also going, it's completely perpendicular to that. So hopefully you can see what sigma d looks like. And that's going to wrap up all of these sigma planes of symmetry. Okay, so let's now talk about this guy, Sn. What it says for you to do is do a Cn rotation, follow it with a flip through whatever rotation axis you had, then reflect it about an axis. Now, something that you need to note is that Cn does not have to exist, and OH or sigma H does not have to exist either. They just don't, okay? Because you're doing two operations in one in this very special sort of symmetry, you just don't need it, okay? And you're going to see that C4 does not exist here. C4 does not exist. If I rotate this bond, it's going to bring this group forward, this group back, and these groups just being flat lines. You're going to notice that we're going to have an inversion, okay? That C4 does not exist. But in this case, we're going to try to identify that Sn exists, so we allow this to happen. So notice what happens when we rotate. So this is H1, H2, H3, H4. When we do one rotation of C4, which is a 90-degree rotation, let's say we bring it this way, so clockwise, we're going to notice that H1 comes to the front, H2 goes to the back, H3 now is, so H3 is coming out, it's now in the plane of the board, and such as H4. So notice that. It's not symmetrical. This is not symmetrical, but that's not the point, okay? The point is that we then flip across sigma H to that axis. So sigma H in this case is right here. That's sigma H. So when we do that, we're going to bring H4 and H3 up. So let's draw that. H3, H4, right now they're up, that's sigma H. That's because of sigma H. And now these go to the bottom. We're going to get H1 and H2. And notice because they're all hydrogen, they're all equivalent. So this is a symmetrical symmetrical operation you can do, even though these elements don't exist, okay? That's S sub n. Hopefully that was a good way to show you what S sub n is. But let's keep moving. We also need to talk about this guy I, the inversion operation. And the way I want to show this to you is using ethane. So H1, H2, H3, H1, H2, H3. Okay? So, what the inversion does, or I should actually label these 4, 5, and 6. My apologies. 4, 5, and 6. What the inversion symmetry tells you to do is go through a common point, invert the molecule or invert the atoms, and do you get symmetry? The best way to show this is here's our point of inversion. Point of inversion. And have their trajectories go right through it. So for example, H4 is going to go through the center and end up where H3 is. Subsequently, H3 does the same but in opposite directions, and they all do this. H1 goes where H6 is, and H6 ends up where H1 is, and then same with these guys as well. And what you're going to notice is when you do this operation, you still get hydrogens. So H3, H2, and H1. And you'll also get you'll get H6 up here, H5 in the middle, and H4 down below. And notice this is a symmetrical molecule. If I unlabeled these hydrogens, you would not be able to tell the difference. That is the inversion operation. It's kind of rare and hard to find, but it is allowed. But when you do this inversion through this center point, you have to get back the same symmetry. So it's very tricky to get. You'll see this in octahedral complexes, for example. Let me just draw that if you forget what those are. Right, all of these ligands bound to this 6-coordinate complex metal. It's going to go through and end up on the same sides. Granted, L is all the same, okay? If L is all the same, then that would be allowed. But let's say like this was instead group A, and then you did an inversion, okay, well then that's just not allowed. You can't do that. So I is a very unique one in the fact that it's kind of rare, okay? So I just wanted to make that point kind of clear. Sometimes you'll use it in like if you do successive operations, maybe I is allowed then. Okay, so what about E? And I'm going to say through an origin for that one. E is very easy. It's kind of in the name, right? E for easy. And this one is you don't do anything, quite literally. For the mathematics behind this and in proofs in life, you have to have these trivial things that are true. So for E, you have to have doing nothing gives symmetry. It sounds so dumb because it is. To me, it's dumb. But for the math, it makes sense. For example, if I have this ethane molecule and I don't do anything to it, I get the same thing back. It's just a convention of having to do proofs. Okay, now that we've discussed this, now we have to talk about point groups. You're going to see quite a few of these. And point groups are on a chart. I'll hold it up to the screen, but find this online. I might even link it in the description, so check it out. My notes have it. You're going to see that you can even take a picture of this. You're going to have this flow chart. You start here and you ask questions about the molecule. And you're going to see that, like, let's say, for example, is the molecule linear? Okay. And then let's say you say yes. You go over here. Does blah, blah, does the sigma H exist, right? Remember, that's the perpendicular to the principal axis. Does that exist? Yes, then you have D infinite H, okay? And point groups are just quick things that we can assign that have some meaning. So let's just show one of them, and we kind of already just described it with our flow map. This is going to be C infinite V and D infinite V. So for this group, this is saying C infinite exists on our principal axis. So there exists a point we can rotate the molecule such that there's an infinite amount of rotation. So this has to exist. But infinite sigma V planes exist. Okay? For D infinite V, C infinite also has to exist. Infinite sigma V exists. So you have to have infinite amount of those planes of symmetry somewhere. And you also have to have sigma H has to exist. So sigma H has to exist, and all of these infinite planes sigma V have to exist. So let's just kind of show what this means. Let's say we have carbon monoxide. Okay? We have a principal axis right here, and this is C infinite, because I can rotate this an infinite amount of times and I will still get back the same molecule, or yeah, same molecule, same symmetrical molecule. Notice that sigma h does not exist, right? Because if I made a plane right here perpendicular to the principal axis, C infinite, if I flip this molecule, then O and C get flipped, and they're not, there's no symmetry there anymore. So sigma h doesn't exist, but notice sigma v does exist, and there's an infinite amount of them, because as we begin to rotate, there becomes planes that intersect this principal axis. So the most intuitive one is the one where the molecule is right now, right? And that's just flat. It's encompassing this bond. But as we rotate maybe this triple bond, you might even get ones that are vertical. And notice for all of these different planes of sigma v, they all exist. Every single one you could fit in this circle here exists. So this is like a little cylinder you could think of. A cylinder that is made up of an infinite amount of sigma v's. So yeah, there's an infinite amount of sigma v, and because that's true and sigma h does not exist, this is going to be C infinite v symmetry. Again, you would use your flow chart to determine that, but I just wanted to bring it up here. Hopefully you can see that. If you don't, drop a comment. I can help you out there. But let's talk about a counterexample where we might have D infinite V energy, or symmetry, sorry. And that would be in the case of oxygen, for example. Notice that it's the same C infinite symmetry. I can rotate this as much as I want, as little as I want. I could rotate it 0.000000001 degrees, and it would still have symmetry. So C infinite exists. Does sigma h exist? Yes, it does. Sigma h does exist because if I flip oxygen, the two oxygens, aka I mirror it, I get the same thing back. And notice, just like we said with this one, we have infinite amounts of sigma v symmetry. So sigma v exists, and so does this guy as well. Right, this, so we, and of course this would encompass all planes contained within this cylinder, and all the planes that you could make rotating the plane, so to speak, from this origin here. So everything that this cylinder encompasses of sigma v exists, and therefore this has D infinite v symmetry. Okay, let's do another example, and let's try and use the flow chart to figure out what kind of symmetry we have. So I'm just going to make something up here. Let's say we have a palladium complex with these ligands coming off of it like this. So first, it might be good to find what's your principal axis, all that fun stuff. Do certain groups exist before you get to your flow chart? Well, notice I can just tell this right off the bat. This is going to be our principal axis of C4 because I can rotate it 4 different times, 90 degrees, and I'll get the same thing out each time. So I know that exists. There's also these C2 groups. And there are 4 C2 groups. That's going to become important. If I rotate this molecule over on itself 180 degrees from this ligand, I'm going to get back the same thing. And you could make a model of this if you have a modeling set. And there are 4 of them coming off of each ligand. Okay, notice that sigma h exists. I'm not going to draw it, not to clutter the board, but let's just write that sigma h exists. Notice because our principal axis, we have a perpendicular plane such that if we mirrored this complex, we would get we would get sigma h. I hope that it's pretty obvious that sigma v and sigma d exist. Sigma v because we have these planes, these two planes that go through the axes, they exist. So there's 2 sigma v. Sigma d also exists. We have one that goes through like this. We have one that's going through like this. So there's 2 sigma d. And one more note that I want to make, if you have 2 sigma d planes, you can actually define them. You can say I have, and the notation that's proper for this is, and let me just make sure that you can see this far if I decide to draw that far. We can call it sigma d and sigma d prime, okay? And same with sigma v and sigma v prime. There can only be one sigma h, so we don't have anything for that really. But notice sigma v prime, sigma d prime. And that's coming from the fact that we have 2 of those planes of symmetry, or planes of symmetry in our molecule. Or our complex, I should say. Okay, so let's now assign a point group to this now that we have everything. So here we are again. I guess this would probably be the best way to show it. We start here. Are we linear? Well, I'm going to say probably not. Okay, I hope that we can see that it's not linear. So we go over here. Do we have this one, TD, OH, ID? It's tetrahedral geometry, octahedral geometry, or isoprismatic or something. It's one of those molecules. It's I'll figure out the name. Maybe I'll edit it in. But that would be IH. And the way that you determine that is if you have equivalent ligands and they're in a tetrahedral, octahedral, or whatever that other one is, I forget. If you have it in that sort of symmetry, and it turns out, yes, we do. This is going to be OH symmetry, or octahedral symmetry that has a sigma H plane in it. So that one was pretty easy. Let's say, for example, we turn this ligand into A. So this is a different ligand than L. Well, then C2 goes away. This C2 goes away. This C2 goes away. This C2 goes away. Sigma H drops out. Is that, are we allowed to say that? Yep, sigma H falls out. But there are still sigma V, sigma D. Okay, and please see why that is true, because this thing is not changing its position as we begin to rotate this and thus look at the subsequent sigma V, sigma D planes. So let's go back to our chart here. We start, is it linear? No, it's not. We don't have tetrahedral, octahedral, and that other one because this ligand is different. Sigma H doesn't exist. Okay, do we have a principal C-axis? Yes, we do. It's C4. So we're going to say yes. The next question is, do we have an n number of C2 to Cn? So in this case, when we had the L here, then we had C2, but in this case, we don't. So we're going to say no to that because Cn is this. We would need 4 C2s, which could come from there, but it can't because of A. So we're going to say no. Is there n sigma V to sigma n? Okay, does the number of sigma V, so we have 2 of them, does that equal the number here? Do we have 4 sigma V? Well, the answer is no, we don't. So this symmetry is going to be C4 symmetry. And that's all we can say about that one. So basically what we determined here is the only amount of symmetry and thus its subsequent point group that we assign it. I hope that you found this video helpful. If you did, please drop a like, comment, and subscribe. I hope that you have a wonderful day. And please look in the description. I will post a link to a flow chart, maybe put it on the screen. Just some way get a flow chart because it's very helpful. But with that said, have a wonderful day. Bye-bye.